Good evening, everybody. How's everybody doing today?
Hi.
How are you guys doing?
Terrific. Is my audio okay?
Yep, I got you loud and clear, 5 by 5. I think we'll just let a couple people trickle in here. Um, Edward, if you just want to make like another announcement, like, hey, ground school's going on now. Just, I'm not sure if everybody's 100% knows that it's happening. Thank you, sir. You read my mind. All right, guys. Well, as everybody trickles in, if you're new to the school this week, my name is James, and we'll be going over another lesson this week. And hey, Kevin, just so you know, you got a lot of background noise coming through. Um, introduce myself. My name's James. I'm an instructor here at VATSTAR. If you're new, this week we are going to be going over weather. And a little bit of a disclaimer, this isn't going to be extremely comprehensive, but I'll try to give you the basics. And we can kind of think of it as a crash course on an introduction to weather. You can always go out afterwards, or if you have more questions about it, you can shoot me a DM, or we can wait till the end and we'll go over a lot of the things together. If you have any more questions, I'll try to answer more of your questions. Um, Again, as we go through the slides, if you have questions that pertain to the slide, go ahead and interrupt me and ask your question. No problem doing that. If you're confused about something on a slide, go ahead and ask me. Want to keep this as kind of like an informal environment where we can kind of get to know each other. Um, it looks like we got a pretty good turnout for tonight. So let's go ahead and get started. Like I said, today's lesson is going to be focused on the basic principles of weather. So we're going to talk about the heating of the Earth, circulation and wind, temperature, air masses, atmospheric stability, clouds, turbulence, thunderstorms, wind shear, all the fun stuff that you're going to want to know as a pilot, um, whether it be for P1, P2, or if you're flying in the real world as a VFR pilot or as an instrument rated pilot. So let's talk a little bit about just this basic fundamental of weather. And most weather takes place in the lowest level of our atmosphere, and that's actually known as the troposphere. And that's where all living beings kind of live. There's four levels to the atmosphere. You have the troposphere, the stratosphere, the mesosphere, and the thermosphere. The troposphere being the lowest, the thermosphere being the highest. And most of your active weather is going to be in this lowest level, the troposphere. And obviously, some things like storms will actually come up here into the stratosphere on a very, very severe storm. But that's something basic just to know. Um, so, if we talk about how weather actually works, weather's actually caused by the sun. Every action of weather is because of heating of the earth resulting from the sun. And the reason why we have weather is the sun unequally heats the earth. And that's because the earth is rotating. So you constantly have like one side becoming hot, one side becoming cold. And another thing that plays into that is actually the tilt of the earth. That unevenly heats the surface of the earth. And because of these differences in heat, you get air masses that are heated differently. And they kind of cause weather to start moving. So every physical process of weather is accompanied by or a result of unequal heating of the surface of the Earth. So because of that unequal heating, the Earth actually gets hit with the most direct sunlight here at the equator. So what happens is the air at the equator actually becomes heated up the most. So when air becomes hot, it actually rises. And what happens is the air at the equator comes upwards and circulates outwards towards the north and the south latitudes. And because of that, you get weather patterns that will push air away from the equator. And as you get northern, the airflow starts to cool and come back down and keep getting pushed northbound. And what happens eventually is this air becomes so cold and the weather dissipates. But that basic fundamental is hot air rises and cold air sinks. So that unequal heating of the Earth actually will cause pressure variations. Cold air tends to have a greater pressure because it's sinking, and hot air tends to have a lower pressure because it's rising. And that actually causes the variation in altimeter settings or pressure at different points on the Earth. So we'll look at a map later on where we'll actually see that the pressure around North America or other continents will not be uniform. We'll see that the pressure is changing from point to point. Now, that's good for me to bring up that in aviation, we have a standardized pressure setting that we use for uniformity. And if you notice above transition altitude in a lot of places, you'll switch to this standard pressure so that air traffic control can coordinate you more uniformly above a certain altitude. And that pressure is 29.92 inches of mercury or 1013 hectopascals. That's what's known as our standard pressure. And like we were saying before, that cold air which is sinking has a higher pressure, and that warm air which is rising has a lower pressure. Does that make sense to everybody? Again, if I'm going too fast or you want me to explain anything more in detail, I really urge you to ask questions. I don't want to be going too fast for anybody.
Hey James,
Yeah, sure. What's up?
at what altitude should we switch the altimeter to 29.92?
That depends per country. But if you're flying in the United States, it's 18,000 feet, flight level 180.
Like,
No problem. All right. So you might be thinking, well, shouldn't all weather be moving directly north or south if you have that rising air and sinking air? Well, what happens is because the Earth is rotating, the air kind of gets deflected or dragged with the Earth. So that unequal heating and movement of air is now being deflected, and that's why you get weather patterns. And that large, simple air circulation pattern, greatly distorted, is distorted by the Coriolis force. So, have you guys ever heard, like, if you're in the northern hemisphere and you flush your toilet, it'll go one way, and if you're in the southern hemisphere, it'll flush another way? Have you guys ever heard that before?
Yes,
Yeah, so
that's
that
true.
I don't know if it's actually true. I know that there's been a couple YouTube videos. But toilets, if they're completely, non-jetted or whatever, they'll actually spin a certain direction because of that Coriolis force. And weather acts the same way. So when wind begins to move at higher altitudes when it's rising, that Coriolis force deflects it to the right in the northern hemisphere and to the left in the southern hemisphere. And that actually will cause it to flow parallel to isobars. And we'll talk about isobars in a little bit, but they're lines of equal pressure. So they're lines where the pressure is exactly the same. And if we look at our little diagram here, this blue line represents the direction of air, and the black line represents the path it will actually take. So if air is moving southbound in the northern hemisphere, up in the higher latitudes, it'll actually get deflected to the right. If it's moving northbound in the middle section of the northern hemisphere, it'll get deflected to the right. So it's always getting deflected right in its direction of motion. If you look in the southern hemisphere, it wants to move this way, but it's getting deflected to the left. It wants to move this way up to the northeast here, but it's getting deflected to the northwest, and that's because of the Coriolis force. Does that make sense to everybody?
Roger.
All right. Let's move
That
on.
is not where the equator is, though.
Well, the equator's here at the red line.
But that is not where it is in real life.
It's just a representation, so it might not be
Yeah.
exact. Um, it's just kind of a diagram to give you a general idea. Um, so we're talking mostly for the northern hemisphere here. I'm not going too much into the southern hemisphere as we're a VATSIM USA ATO. Um, so we're going to be talking mostly about the northern hemisphere here. If you want information on the southern hemisphere, most of these concepts are just kind of reversed or the opposite of what they are in the northern hemisphere. So air patterns or air masses in the northern hemisphere follow a certain set of rules. Um, if you have a high pressure air system, which is air that's sinking, the air actually will circulate clockwise. If you have an
What's it?
air, I'm sorry,
Sorry.
if you are you asking a question, or we're just,
No,
oh, okay, all right.
finish my thought.
So if air is circulating clockwise, that means you have a high pressure system. If you have a low pressure sinking air mass, that air is actually going to circulate counterclockwise. And we'll get into why this is important on the next slide. Um, it has to do with ground speed. But another thing to remember about these air masses is the closer you have isobars together, you'll have a greater wind speed, and that's basically the closeness or the tightness of pressure gradients. Um, but one other important thing to remember is that your local wind patterns might not necessarily exactly follow wind systems. And that's because the friction of the earth or the surface friction may deflect air in different directions. So if you have an air mass that's generally blowing air to the east, um, depending on what the terrain is like, you might actually deflect that air to the north or northeast. So you might see that wind is slightly shifted because of geography. So let's talk about why that knowing which way the wind spins is important. So if you're going from A to B, right, San Francisco here on the west coast of the United States to JFK here on the east coast of New York, if you were to go direct from A to B and you had a low pressure system here, well, you're going to have a wind blowing against you the whole time. You're going to have a super strong headwind delaying your flight time. But if you slightly go off course and take a route which is slightly to the south here, you're going to have tailwinds the higher time. These high pressure systems here are rotating clockwise and they're going to blow you across the south. And this low pressure system here in the center is going to push you faster to New York. So you're going to have a tailwind the entire time and actually decrease your travel time. So sometimes going direct is not actually the fastest route somewhere. It might be the shortest distance over the ground, but because of weather patterns, you might actually increase your total travel time. And that's why it's important that we look at the direction of winds going from point A to B. Now, if you're going from B to A, it makes more sense to go direct. But again, it varies depending on where the pressure systems are, and that's why you want to look at a surface analysis chart. And I believe I have one in here later that we'll look at. So let's talk about temperature a little bit. In aviation, temperature is measured in Celsius, and the standard temperature at sea level is 15 degrees C, and that's 59 degrees Fahrenheit. And we have this standard temperature in order to relate it to other things, because when you're planning, you'll be given all your values as if it were standard temperature, and you will adjust those values depending on what the actual temperature is. So the standard's kind of like a baseline for all your performance numbers, and you'll change them regarding on what the actual temperature is. So on average, or in general, temperature decreases with altitude by 2 degrees Celsius per 1,000 feet. And this is what we refer to as standard lapse rate. And lapse rate is simply the rate at which temperature is changing as you increase altitude. Now, since this is an average, the exact value seldom exists. In fact, in rare cases, temperature actually may increase with altitude, and that's what we call a temperature inversion. Now, this diagram here actually shows you this. So, in normal conditions, you'll have warm air below, and as you increase, you'll get colder air, and you'll eventually get very cold air as you increase altitude. But sometimes you'll find cooler air, but you'll have an inversion layer of warm air, which is basically a warm air layer on top of a cold air layer. And as you increase altitude, it'll get hotter. But once you pass through the inversion layer, it'll begin to decrease in temperature again. And these inversion layers typically cause a reduction in visibility. We'll talk about these in a little bit. Let's talk about moisture now. Air has moisture in it. You guys ever walk outside and been like, "Damn, it's really hard to breathe. It feels like I'm breathing in water." Anybody ever feel like that? I mean, I know if you're in Southern America, you'll definitely feel that a lot. I'm not sure what the temperature's like in the UK or Australia or wherever you guys are from. Um, Anybody feel like it's really muggy outside?
Roger.
Well, usually that's because you have a very high relative humidity. But water vapor can be expressed in two different ways in the air. And the commonly used terms are relative humidity and dew point. So, relative humidity relates to the actual water vapor present in the air. in relation to how much water the air can actually hold. So air can be actually multiple different temperatures. So if you have air that's 75 degrees, it can hold much more water than air that's 20 degrees because the air particles are much more separated. They can hold more water as temperature increases. So relative humidity is the amount of water in the air in relation to how much water it can hold. And if you look at the diagram here, the white here represents how much water could be held at 55 degrees and how much water is actually in the air. So here we're holding 50% of the possible capacity. Now, if you look at 44 degrees, the water amount has actually been unchanged, but the amount of water the air can hold has decreased. So you've increased the relative humidity. So as the temperature decreases, even though the water amount or the water vapor content has remained unchanged, the relative humidity increases. And as you get to 37 degrees Fahrenheit, the maximum possible water vapor is now 100% relative humidity. Now, this is where dew point comes in. And dew point is the temperature at which you must cool the air to reach 100% relative humidity. And that's the point at which you'll begin to get rain, you'll get fog, you'll get clouds, because the water can no longer hold the air can no longer hold the water, so it actually condenses into the atmosphere. Does that kind of make sense to everybody?
Yep, yep.
Yep.
All right, wonderful. So, we're going to move on to air masses now. So there are four main types of air masses, and air masses tend to take on the properties of the regions in which they form. So if you're in a very tropical region, like you're in Cancun, Mexico, Cancun is kind of on the water, it's kind of on the continent. Well, the air masses typically form south of Cancun. So an air mass that forms in like central Mexico will be very hot because it's in a tropical region, but it's over the land. So there's no moisture for the air to pick up. So that air is going to be very hot and very dry. So we call that a continental tropical air mass. A continental polar air mass is an air mass which forms in the northern latitudes or the very southern latitudes, and they form over land. So what happens? Um, what happens is as you go to the polar regions, you have very cold, dry air when it's formed over a landmass. You can also get maritime polar air, which is formed in like the Pacific Northwest upwards by Alaska. You have air that's over the water but very cold, and it picks up moisture, and that will move inland, and that's called a maritime polar air mass. Maritime tropical air masses, as you might have guessed by now, is air that's formed near the equator over water, and that's a very warm, moist air mass. So those are the four types of air masses, and we'll talk about how they relate to weather in a little bit. So, ridges and troughs. So a ridge is a elongated area of high pressure. So if we look here, we can I don't see any ridges here, but it looks like here's a ridge. Or maybe I'm getting my legend reversed. Let's double check. So that's actually a trough. Where's the ridge on this chart? Why is it not popping up for us? Yes, okay, so that's actually a trough. So here we actually have a trough, which is an area of low pressure. And we have another trough here. It doesn't look like we have any ridges on this chart, but a ridge is an elongated area of high pressure. It'll kind of be like this, except it'll be high pressure. And a trough is an elongated area of low pressure, which we see here on this surface analysis chart. Now, we're going to talk about fronts in a little bit, and fronts are basically the boundaries between air masses, and those are always in troughs. So here you can actually see we have a front, which is in this trough. And here we have another front, and it's in a trough. So now we're going to talk about the legend or fronts. A cold front is a leading edge of an advancing cold air mass. And a cold air mass is typically a high pressure system because high pressure is usually descending air and it's usually colder. A warm front is typically hot, low pressure air, and it's the leading edge of an advancing warm air mass. Warm fronts typically move about half as fast as cold fronts. And this legend I put in here is the legend for the chart we saw on the previous page. So these are all the types of weather. Here we have a cold front that's indicated by blue with triangles. A warm front indicated by red with half circles. A stationary front, which is a front which has stopped moving, is indicated by half triangles, half circles. An occluded front is triangles and circles on the same side, which are purple. And a front that is changing is indicated with these black lines here. And then these are typically not as important for pilots, but they're indicated on the chart as segmented lines of the related front.
What is an occluded front?
An occluded front is a air mass. How do I describe this to you in basic terms? It's essentially a cold front on top of a warm front. I'm trying to think of a better way to describe this to you. It's essentially a combination of a warm and a cold front, if that makes any sense. It's kind of like an intersection of where a warm air mass and a cold air mass overlap with each other.
But they're different heights.
Sort of, yeah. It's the best way I can describe it to you in layman's terms. But it's just kind of like an overlapping area of where warm air is on top of cold air is on top of warm air. But it's not the entire air mass.
Okay.
We'll continue talking about fronts. So cold fronts, which are those blue triangles, typically produce the following type of weather. Not always, but they can come with this type of weather. You'll normally with a cold front get gustier winds, hail, lightning, or thunder. You might get heavy rain, or you could get a drop in temperature because it's cold and there's a cold air mass behind it. Warm fronts typically produce this type of weather. You'll usually get gentle rain or light snow. It'll usually be preceded with lighter weather, milder weather, and you'll typically get a rise in temperature. And what I showed here in this diagram is a cold front. So this cold front is following a low air mass, a low pressure air mass. And what I've shown here is a storm cell. This is called a squall line thunderstorm, and this leads you typically a cold front, and it's a series of very severe thunderstorms ahead of a front. And what you'll see is basically just a line that has massive thunderstorms. And I don't know if I included a photo. If not, at the end, I'll show one. This here is an occluded front, so there's probably a high air mass somewhere over here that we can't see where that's overlapping. And that will typically have a combination of either of these weathers.
The triangles are pointing in the direction the front is moving?
Exactly, yep. So this front is moving from here in the northwest to the southeast.
Okay.
James, wasn't the top one stationary front instead of an included front?
My bad, yep, I misspoke. That is a stationary front. Yes, you are correct. Thank you for catching that. So let's talk about stability of the atmosphere, and this is really what's important for weather. It determines basically how fast air is rising, or the air's ability to resist movement is the stability of the atmosphere. A stable atmosphere is typically a cold pressure atmosphere because you have air that's sinking and usually more stable. But a stable atmosphere resists upward or downward movement. So it resists turbulence, it resists convective activity, and convective activity is basically vertical motion, which you get with thunderstorms. But an unstable atmosphere allows upward or downward disturbance to grow into vertical or, like I said, a convective current. So let's talk about some of the properties of an unstable or stable atmosphere. When you have unstable air, which allows vertical development, you'll typically get cumuliform clouds, which we'll talk about in a little bit. And those are like the puffier clouds, thunderstorm clouds, cumulonimbus, cumulus clouds, all the different types of cumulus clouds. You'll typically, with unstable air, get showery precipitation. So you'll get rain that's kind of on and off. You'll usually get rough air or turbulence, and typically, which people kind of get confused on this, unstable air will actually give you the greatest visibility. except in blowing obstructions. So, like if you have a sandstorm blowing in, which is unstable, that obviously is going to reduce your visibility. But unstable air tends to give you good or great even visibility. Stable air, on the other hand, will typically give you like those flat stratus clouds. Like a solid overcast layer would be an example of a day that's very stable. Uh, with stable air, you'll typically get continuous precipitation. So if you notice it's raining all day, it's usually probably a very stable air mass with a lot of stratiform clouds. You'll have very smooth air on these days because there's no vertical motion. And on these smooth days, you'll actually get poor visibility because fog might form or just rain might be causing a reduction of visibility. And you'll get haze or smoke, usually less smoke, but more haze. And that's kind of the properties that we can expect to see from these two different types of air. So now we're going to talk about clouds and how that relates to stable and unstable atmosphere. So stability, like we talked about, actually determines what types of clouds will be formed. Cumuliform clouds or stratiform clouds. Cumuliform clouds are those billowy type clouds that kind of look like a big pillow or like a puffy, marshmallow. And they have considerable vertical development, which means they extend from low altitudes to high altitudes, or just they have a great variation in altitude. And they actually enhance the growth rate of precipitation or rain or snow or any other kind of precipitation. They're formed only in unstable conditions, and they produce showery precipitation made up of large water droplets. Stratiform clouds are those flat, more evenly based clouds formed in stable conditions, like a solid overcast layer. And they produce steady, continuous light rain and drizzle made up of much smaller raindrops. So here's a good diagram to kind of describe those clouds. So if we were looking all the way on the right here at this cumulonimbus cloud, we have a lot of unstable air being developed right now because that unstable air allows air to be pushed upwards and form this thunderstorm. So cumulonimbus is a cumuliform cloud, and nimbus means rain in Latin. In Latin, I believe. So this is a vertical development rain cloud or a thunderstorm cloud. Here you have the typical cumulus cloud. It's kind of like a puffy marshmallow. Here you have your flat stratus clouds, and these are typically very stable. Here you have nimbostratus, which are stable rain clouds. So they're rain clouds that are in a stable atmosphere. You have the higher level altostratus clouds, which are the flat, stable middle clouds. Altocumulus are those vertical development cumulus clouds that are in the middle. Then you have your cirrus clouds, which are the very high level clouds. You can have the kind of uniform cirrostratus. You can have plain cirrus, which is like a combination of the both. And then you have cirrocumulus, which is the cumulus clouds that are high up. So these are the primary family of clouds. Obviously, you have variations on all of these, and we could go into hours about the different types of clouds. There's a study dedicated just to clouds. But for you as a pilot, just recognize that puffier clouds tend to be associated with unstable air, and flatter clouds tend to be associated with stable air. So let's get back to how relative humidity applies here to how clouds are actually formed. So if you think about how the temperature decreases as you gain altitude, uh, at some point, the temperature is going to reach the dew point of the air because the air's cooling as you climb. And because of that, you can actually figure out what altitude the clouds are going to form. Um, so the base of a cloud, which is formed by vertical currents, so this is really more applicable to those cumuliform clouds in unstable air. You can roughly calculate the base by dividing the difference between the temperature and dew point by 2.5 and then multiplying the result by 1,000. So this is the dew point lapse rate, which is 2.5 degrees Celsius per 1,000 feet. So here's a little problem to kind of explain it to you guys. If the surface temperature is 15 degrees Celsius, so you're at an airport and the METAR is indicating 15 degrees Celsius, but it's also indicating that the dew point is 10 degrees Celsius. So we take the difference of these two. So 15 minus 10 is 5 degrees Celsius. So the difference between the temperature and dew point is 5 degrees Celsius. What we do is we take that difference and we divide it by 2.5 degrees Celsius and we get our cloud base. So this is the math. We take 5 degrees Celsius, divide it by 2.5 degrees Celsius, and we get 2. Now 2 times 1,000 is 2,000 feet AGL. So we can actually figure out roughly that the clouds will form at 2,000 feet. Does that make sense to everybody?
Just a question. The dew point is then a measurement of how saturated the air already is.
The dew point is the temperature at which you must cool the air to reach 100% saturation. So the dew
But
point,
basically, when it's raining, the dew point is the same as the actual temperature.
yes. In a perfect world, yes, that's correct.
Okay.
So the bigger the difference, the higher the clouds would be.
Yes, exactly. So if this was 20 degrees, if it was 20 degrees Celsius at the surface and the dew point was still 10, so you'd have 10 divided by 2.5, which would be 4. So the cloud base would be at 4,000 feet, AGL.
Could there be a large difference with no clouds?
There could be, but if it's stable air, you won't you might not have clouds. This is typically for stable unstable air. But it's not always the case. This is just like a rough calculation to know. If you're at an airport that doesn't have cloud reporting information and it just gives you temperature and dew point, but you really need to know what the base of the clouds are, this is like some quick math you can do to figure it out.
Thank you.
Sure. Just wanted to kind of give you guys an example of how you can apply these concepts. Let's talk about turbulence now. So, if you had to guess, and I'll ask this as an open question, when do you think turbulence is most prevalent? When it's stable or unstable?
Stable.
Unstable.
Unstable.
Unstable, right? Because when it's unstable, you have a lot of moving air. It's moving up and down very rapidly, or just in general moving up and down. So cumulus clouds, like we talked about before, are formed by convective currents, and convective currents are rising and descending of air, or heating from below, which causes air to rise, and then when it goes up top, when it rises in the atmosphere, it cools and then it sinks again. So it's rising and descending air. Therefore, a pilot can expect turbulence inside cumulus clouds because cumulus clouds are made up of unstable air, and then also below cumulus clouds because they're being heated from below. Uh, Especially tower and cumulus clouds. Now, I'll say this: if you're flying in a tower and cumulus cloud, you have bigger problems because you're inside a thundercloud, basically. Uh, so if you end up in that situation, I wish you luck, really, because I don't think you're going to get out of that situation. If severe turbulence is encountered either inside or outside of clouds, this is critical. The airplane's airspeed should be reduced to the maneuvering speed, and we talked about maneuvering speed either last week or the week before. And the pilot should attempt to maintain a level flight altitude. Here's what's critical: do not attempt to maintain your altitude. You're not going to win in a fight against turbulence, because you're going to be going up and down in unstable air, and if you try to maintain altitude, you're going to end up in a stall. So it's important that you just try to maintain level flight when you're in turbulence. Any attempt to maintain a constant altitude, you're greatly increasing the stress on the airplane and you risk damaging the airplane. So when you're in unstable air, just remember, focus on maintaining a level flight attitude. Does that make sense to everybody?
Yeah.
Awesome. Okay. All right, let me take a sip of water and we'll get in the thunderstorm. So, what does that look like to you guys?
Cumulonimbus.
That's exactly correct. So,
An anvil.
exactly. I was just about to mention that. So, this looks very familiar. If I were to like Photoshop an image of an anvil over this, it would kind of be like an exact picture. So, I can already tell from a couple years of being a pilot that this is a thunderstorm, and it's kind of cool because if you're actually flying IFR and you're avoiding thunderstorms, if you're 50 miles away, you can see this. Now, if you guys had to guess, what do you think the top of this thunderstorm is?
20,000
No, we'll
feet.
go 20.
20. Okay. All right. Any other guesses?
Where the jet stream is.
Okay. Any others? Any final answers?
Like 40.
Okay. All right. So actually, it can actually range from 40 to 65,000 feet, these thunderstorms, which is crazy. So this one is probably, this looks like it was taken from a jet, maybe at 30,000 feet. So this is probably right around 45,000 feet, the top of this one. But if you look, you have that extensive vertical development, and this is a pretty big thunder cell. And you have the characteristic of a thunderstorm is this anvil top, where you have kind of an anvil shape, and then you have, uh, the main part of the thunderstorm here, but then it goes up and it starts to make an anvil. So this is a pretty easy way to recognize thunderstorms, and when it's an individual cell like this, it's pretty easy to spot. Now, the scary thing is these storms and these anvil tops can be embedded in a giant layer of clouds, and you'll never see them. The only way to see these is with radar, and that's when it becomes really scary. So thunderstorms actually present many hazards to flying, as you may have guessed. Three conditions are necessary to form a thunderstorm, and that is sufficient water vapor, an unstable lapse rate, so a very quick variation in the lapse rate, and an initial upward boost. Now, that can be heating from below, it can be a cold front or a warm front lifting the air up, or it could even be mountains. I mean, mountains are massive. They can push air upwards. If you have cold, moist air, or warm, moist air, and it gets pushed up with a mountain, that could turn into a thunderstorm pretty easily. And that vertical development creates unstable air, which creates those massive convective currents, which create thunderstorms. And there are three stages to these thunderstorms, and there's only three stages. There's the cumulus stage, which is the developing stage, the mature stage, which is the main stage of the thunderstorm, and the dissipating stage, which is the end of the thunderstorm. So the first stage is the heating and rising of the thunderstorm. So you get all this air that gets pushed upwards, and that's called the cumulus stage. And eventually, the air will make its way up, and clouds will form up to 40,000 feet. And what happens at 40,000 feet is the air begins to cool and then force its way back downwards. And what happens is, at this point, the air is condensing so much it's forming rain and water droplets. And when that rain comes back downwards, it creates all this precipitation and forces it back downwards. So the mature stage of the thunderstorm is the main stage of the thunderstorm, and we characterize this stage or tell its beginning by the beginning of precipitation. So as soon as precipitation begins to start in a thunderstorm, that's the beginning of the mature stage of the thunderstorm. Now, something else to remember. Lightning is always associated with a thunderstorm. If there's not lightning, it's not a thunderstorm. And lightning is caused by static electricity and the differences in static electricity between the highest layer of the clouds, the lowest layer of the clouds, or between the bottom of the clouds and the surface of the terrain. And another thing that's formed in the mature stage is you actually get hail. So hail's formed inside those thunderstorms by freezing, melting, and refreezing of water as it's carried up and down within the thunderstorm. And eventually it gets so heavy that the thunderstorm can't keep it within itself and it drops to the surface. The final stage of the thunderstorm is the dissipating stage, and that's actually when the thunderstorm will begin to collapse on itself. It can no longer maintain energy, there's not enough heating from below, and all the air begins to cool down and eventually will collapse in on itself, and the thunderstorm will just end. And that's why you notice sometimes thunderstorms just kind of disappear. It's because all the air is so cold, there's no clouds anymore, and well, you get no precipitation, and the storm just kind of ends. And so that's when you'll begin the ending of rain. Most of the rain will start to light up or let up, and you'll see the end of the thunderstorm. And it'll just kind of disappear. If you look at states like Florida, where it's very hot and very unstable most of the day, they have thunderstorms that come in for 10 minutes and then are gone. It's crazy. I did some flying in Florida over the summer, and I'm in a tiny little rinky-dinky Cherokee, and I'm flying around, and I'm flying down the east coast of Florida, and ATC says, "Hey, look out! There's a thunderstorm building right off your right wing." And 10 minutes later, I'm past it, and the thunderstorm's gone already. It's kind of ridiculous and insane how quickly these thunderstorms can develop, but they are a real danger. You have to avoid them.
Is there always hail within a thunderstorm?
Is there always what? Hail?
Hail, yeah. It obviously doesn't come down all the time, but within the cloud, is there hail all the time?
Not I would say most of the time there's a small amount of hail. Obviously, it doesn't always come down to the surface. But I do believe the risk is always there. Like if you're flying through the cloud, I believe you're at a greater risk of receiving the hail. Then again, you should never be flying through a thunderstorm.
Okay.
So, another thing, we're talking about all this convective air and this convective activity. Well, in an unstable atmosphere, right, you get a lot of motion and you get a lot of air that's constantly changing direction, and that's called wind shear. And the definition that I have written here is wind shear is a change in wind direction or speed, and or speed over a very short distance. And this can occur at any level of the atmosphere. This can occur at 1,000 feet. This can occur at 45,000 feet. It doesn't matter. It can happen anywhere. Um, and a pilot should always expect this hazardous and invisible phenomenon uh, operating anywhere near a thunderstorm. And typically it's within 20 miles, nautical miles. You should expect this. That's the greatest risk of wind shear. However, there is another thing called low level wind shear, and you'll get this when it's very gusty, when you have very strong pressure gradients, which is when we talked about before. The differences in pressure are very close to each other, or isobars are very close to each other, aka the pressure gradient is very large. So that wind shear can be expected during strong temperature inversions, which is when it gets hotter as you increase in altitude, or on all sides of the thunderstorm and directly below a thunderstorm. Again, I strongly advise you don't fly anywhere near thunderstorms, even jets avoid them. Low level wind shear can also be found near fronts, so cold fronts, warm fronts, because when when crossing a front, you're actually getting a difference in pressure and wind because you're changing over to a different air mass. So because of that, the wind is shifting direction, and henceforth you're getting wind shear. Does that kind of make sense to everybody?
Yeah.
Awesome. Okay. So, big hazard. Anybody here pick up the new Microsoft Flight Simulator?
Roger.
Yeah.
Yeah.
How do you guys like it?
Fantastic, man.
Yeah. Something cool they added, which I haven't seen in any other simulator, is they added icing, which is actually really cool because this is something that I'm assuming most pilots have experienced in the real world. So it's great that they finally added it default into the simulator. So you might be thinking, well, this is really cool to have in the simulator. Well, it's interesting to have, but icing is probably the single biggest risk to any pilot. And I know I said thunderstorms are bad. If thunderstorms are bad, icing is 2 times as worse. Because there's no pros to having icing. There's only negative effects. So structural icing, I'm not going to talk about engine icing, but because we talked about that in the aircraft systems lesson. Structural icing occurs on an aircraft whenever supercooled condensed droplets of water, so not exactly ice, but the water's cold enough where it will freeze on impact with metal, make contact with any part of the aircraft that is also at a temperature below freezing. So if it's very cold out and you're flying in the winter and you go into a cloud, which a cloud is supercooled water, that water or vapor is going to freeze onto your wing. It's just it's science. You have two very cold liquids, or you have a liquid that's going to freeze onto a very cold solid, and that's how you get ice. And in the in-flight condition, like I said, necessary for icing to form is visible moisture. So, what's the definition of visible moisture? You guys want to take a guess at this?
Cloud.
Okay,
A cloud.
a cloud's a good example. Do you think anything else?
Fog.
Okay, yep, fog.
Rain.
Exactly, and rain. So you basically have the 3 types. You have fog, rain, and I guess rain is another. I mean, snow is another form, but I wouldn't advise flying in snow in a GA airplane because they don't have icing protection systems. But one thing for the P1 especially is icing in precipitation or rain is a concern to you guys because it can occur outside of the clouds. You don't so for a VFR pilot, you can fly in rain. There's nothing that says, "Hey, you can't fly in the rain." You can't fly in clouds, so you need an instrument rating for that, but you can fly in rain. But the problem is if it's cold enough, that rain is going to become ice. Um, so let's talk about some of the problems with icing. If we look at this diagram here, let's look at some of the negative effects. So as ice builds onto your wing, the lift lessens. If ice is icing onto your propeller, you reduce the amount of thrust the propeller can make. ice is very heavy. Water is not light. So if you're picking up, extra weight on the airplane, you have less lift. You've now increased the weight, so you've doubled the effect, and you're also increasing the drag on the airplane because that ice is not smooth. And if you look here on the right, there's two types of main ice. There's actually three, which is a combination of these two. Clear ice is hard and glossy, which is it's literally clear. It's like it's like one of those solid ice cubes that are clear that they put in alcoholic drinks. The temperature ranges from 0 to negative 15 degrees Celsius. They're typically formed with large water droplets, and they're in unstable air or cumuliform clouds. Rime ice kind of looks like frost. It's not really see-through. It's more looking like snow. It happens from 0 to negative 10 degrees Celsius. It's formed from small water droplets, and you typically get it in those stable stratiform clouds. Does everybody kind of get that concept?
Yeah.
Now, there is a combination of these two where you'll get both. You'll get big chunks of clear ice and small little rime ice because and that's called mixed ice, and you'll typically get that when it's like a combination of stable and unstable air. Let's take a look at some of these on real airplanes. Here's a Cessna 172. Look at this. Do you think that this pilot made a safe decision flying in this kind of air? I mean,
Yeah, sure.
Only if he wants to die.
exactly. I mean,
No,
look.
absolutely.
So if you're trying to talk about smooth airflow over an airfoil, that is not happening when you have all this rugged air all over the swing. I mean, look, the ice flows all the way down the back of the airfoil. It's flowing on the struts. It's on the windshield. It's probably on the propeller. And other problems, if you don't have pitot heat on an airplane, you're going to freeze over your pitot tube, which you're going to lose your airspeed indicator. And if you have air moving over this rugged surface, it's not even going to stick to the wing. It's just going to fall off, and you're going to stall. So you're heavy, you can't maintain lift, so you're going to stall, and you're going to fall out of the sky. So a general piece of advice from me to you, just stay out of icing. Look at the freezing level or the temperature at which it's going to be freezing, and you can get that by taking the lapse rate, which is 2 degrees Celsius, and finding where the freezing level is. So if it's if it's 14 degrees at the surface, what's 14 divided by 2? It's 7. So you know the freezing level is probably around 7,000 feet. So if you see clouds above 7,000 feet, well, don't go flying into them. Or if you see rain above 7,000 feet, don't fly into that. You're going to get icing. Here's a Twin Otter, it looks like. That's got some pretty serious icing. This is structural icing. This has de-icing boots. Again, not ideal. Even structural icing adds weight. But that's just another example. Let's talk about frost a little bit. So frost is ice which is formed because of sublimation on the surface. It's not caused directly by flying. This kind of happens when you're on the ground. And what happens is the air may have moisture in it.
What is sublimation?
I'm sorry, what was that?
What is sublimation?
Sublimation is when gas from when air turns directly from a gas to a solid. It's the opposite of. I'm sorry. Yes. So sublimation is either going from a solid to a gas or a gas to a solid. It's either direction.
It jumps the liquid phase.
Exactly. Yes.
Yeah.
So what happens is the moisture in the air that's a gas actually will stick to a surface that is colder than freezing, and it's also below the dew point. So the dew point has to be below 0 degrees Celsius, and the temperature of the surface has to be below the dew point. And what happens is this frost will stick to the wing, and it will develop on the wing over time. And frost causes early airflow separation from the wing because the air can't smoothly flow over the wing, so it just ends up flying off the top. And you will lose lift. So it's important that you remove frost from all the lifting surfaces of an airplane before flight, or it may prevent you from even becoming airborne at all. So that's just one of those things that you're not really going to know in the sim, but it's a good general rule to know.
Just like
So let's talk about fog. We talked about clouds. Fog is just clouds, but they're clouds which are formed on the surface. And fog is a surface-based clouds which restrict visibility, composed of either water droplets or ice crystals. If they're made up of ice crystals, don't go flying in them. Fog may form by cooling of the air to its dew point, so the temperature decreases so much where the air can't hold the water anymore and the fog condenses, or you add moisture to the air near the ground. And fog is classified by the way it's formed. Now, there's 5 types of fog. Now, this is going to be a little bit much, so if you have questions, go ahead and ask me. The first type of fog is called radiation fog or ground fog, and it's formed when the ground is very cold. And what happens is air that may be warm and moist will be cooled to the dew point by the ground because it takes on the properties of the ground. And when the air is cooled down the dew point, you get fog that forms on the surface. That's the first type. And that typically happens at night when the ground is very cold. Advection fog is formed when warm, moist air, so typically air coming in from the ocean in the winter, because the ocean's typically warmer, uh, moves over a colder ground or colder water, and that again cools the air down and creates fog. Upslope fog is when air, and let me foremention that upslope fog requires wind to be pushing air. Upslope fog is when you have moist air that's not at the dew point yet. It gets pushed upwards and the temperature decreases. So as it gets pushed up a hill or a mountain, it's getting pushed upwards where the air is cooler and the air decreases its temperature, and that water turns into moisture and creates fog. So that's kind of fog being created by air being pushed uphill. Precipitation or rain or drizzle induced fog is most commonly associated with fronts or frontal activity and is formed by relatively warm drizzle or rain falling through colder air. So as that cold water falls to the air, it cools the air around it and creates fog. And the final type is steam fog, and this literally looks like steam. It's when you have cold, dry air pass over relatively warm ocean waters. It's pretty cool if you look up a video of it. I'm not going to do it here. But if you look up a video of it, it actually looks like the water's steaming. It's kind of crazy. Does anybody have questions about these 5 types of fog? If you're interested in more in it, I could try to pull up some videos after we finish. But
What's the most common type of fog?
The most common type of
the most common that I've seen, again, it varies with the area. If you're on the west coast of the United States, you typically get a lot of upslope fog. In like the central United States, you typically get a lot of radiation fog. And if you're on like a coastal area, like East Coast US, or I live on Long Island in the United States, we typically get a lot of advection fog, which is a lot of fog moving in from the water. So I wouldn't say there's a very common type of one. It kind of depends on where you're located. So you'll have a more common type depending on where you're located. Does that answer your question?
Yes, sir. Thank you.
Okay. But another thing I should mention is you have to be careful because some of this fog, like upslope fog, can actually cause low-level turbulence and wind shear. So you have to be careful when operating this kind of weather. But other than that, I'm glad to say we're done for the day. So thanks for coming, guys. I hope you enjoyed this little kind of crash course on weather. At this time, we're going to finish up. If you have any questions, go ahead and hit me. Otherwise, I will see you guys next Friday.
Thank you so much.
Thank you.
You're welcome.
Have a good weekend.
You too. Enjoy your weekend.
Yeah, thanks,
apologize.
man.
Yeah,
That
thank
was,
you. I would like to come back to this the dew point.
Okay.
How you might describe it in your own words, by your own definition. Like,
How would I describe dew point in my own terms?
yes, sir.
Okay. Let me think about this. So, I mean, the way it's described is kind of the best way to describe it. So, if you have, let's say the air temperature is 15 degrees, right? Now that air might be holding 80% water. So let's say that air is filled with 80% water. If I decrease the temperature of the air to the point, because as you decrease the temperature of the air can't hold as much water. So while I'm leaving that 80% of water in the air, as I decrease the temperature, the percentage of water in relation to the air is increasing. And that's what we call relative humidity. So At 15 degrees, let's say the air is holding 80% water. As I take it down to 10 degrees, or 13, let's say 13 degrees. Let's say I take the air down to 13 degrees. The water in relation to the air is now at 90%. Let's say I take it down to 10 degrees. Well, now I'm at 100% relative humidity. So we can say that the dew point, or the point where the air becomes 100% saturated, is the dew point.
Yeah,
That
all right. Yeah, I think it does make sense. Thank you very much indeed. Just is a bit related to this sudden alteration of the humidity and wind and temperatures, which the currents are coming, which way and so on, right?
I'm not 100% sure what you're asking.
No, I mean the dew point is a bit relative. It's not that
Yes,
predictable.
yeah, no, the dew point can change. Yes, yes. It depends on a lot of conditions.
Right. So we're coming here to the next part of it. So like, how much does it affect the flight itself? Like the VFR one first. And which point, like those examples that you gave already, like at which point how much they might do harm, or
Like at what
be in
point? At what point does it become a problem?
in a way, yes, or
So so when you get to that dew point, um, typically you'll see clouds form or rain. So that can become a hazard. If it's in a winter and you're at that dew point, if you have rain, then you have to worry about icing. So it's kind of important just to know that at what altitude you'll reach the dew point.
It's a bigger deal if you're flying VFR.
Exactly. If you're IFR and when you get into instrument flying, this becomes a lot more important. So for VFR, it's good to just know the basics and understand how it works. But typically, you're going to be avoiding flying in rain and clouds. So it's not as important. It is good to know how to avoid icing and rain, and that's why you have to understand where rain will develop, and you can understand that by knowing when the air will cool to the dew point. Uh, but for P1 and especially VFR flying, it's not that important.
crystal clear, sir. Thanks a lot.
No problem. Anybody else?
Yeah, I had a question about the when your calculation for the cloud-based thing, where you do the difference between the dew point and temperature and
Yep.
that stuff. Is that? I think I heard you say that might also be an indication of where icing might start.
It's possible, right? So if that dew point, right, it won't always be freezing. So if it's above, 35 or 37 degrees Fahrenheit, or I'll use Celsius. If it's above 5 degrees Celsius, then you don't have to worry about icing. But let's say, it's 0 degrees outside and the dew point's negative 5 degrees Celsius. If the cloud base is at let's see, so 5 degrees, 2. So if the cloud base is at 2,000 feet, that means it's going to be negative 5 degrees at 2,000 feet. So you might experience icing at those altitudes. So if there's clouds at 2,000 feet and it's below freezing, then you have to worry about icing. That's kind of the point I was making.
Understood.
But that temperature dew point spread won't always be below freezing. You just have to worry about icing if there's moisture below freezing. Anybody else?
Yeah, perhaps this is a bit more not that accurate question, but so icing is due to those snowflakes before, or where they're almost becoming a rain wave. So at the condensation of humidity of within the altitude.
Well, not always. So it typically depends, right? Because condensation won't always freeze. So when that temperature reaches the dew point, that doesn't mean you're going to have icing. You can fly through rain as long as it's above freezing. The problem is it's good to know the temperature and dew point if it's below freezing, because one, you can get an idea of where the moisture is in the atmosphere, and if it's below freezing, you know where to avoid the icing.
All right, great, thank you.
how even the distribution over of the dew point in different layers of the atmosphere? Like it might change from how humid it is around the airport or when you go up.
Right. So typically you can figure that out with different forecasts. So you look at METARs; they'll give you the dew point for. The thing is dew point's lapse rate is about the same as the air's lapse rate. So as you increase altitude, the dew point should stay the same, and they should kind of get closer with each other. So as you increase altitude, eventually they'll converge with each other. That's why it's a rough estimate, not an exact estimate, because again, like you said, the atmosphere is always changing, and these aren't exact numbers. It's just kind of like a rough calculation to know.
But yeah, if a front moves in, the saturation of the air can be higher on higher levels than on lower levels.
Exactly, yeah. So
yeah.
the temperature and dew point are always changing. So it's
Yeah,
not always going to be exact.
Yeah.
All right, guys. Well, it looks like we hit an hour, so I'm glad all you came. Oh, you got one more question?
Yeah, man. Sorry. I thought I'd wait right till the end. I was first up. Thanks for that. That was very informative. Fantastic presentation there. The previous lessons, are they available on somewhere else, YouTube's perhaps, or something like that? That's question one.
So,
cool.
The previous lessons are at youtube.vatstar.com, and that'll take you to our YouTube channel. All 4 previous lessons are on there.
Awesome. We'll definitely check those out. And the next one I had was a bit of an obscure one, I guess. Pressure difference between either side of a front. Would that affect your barometer much, your altimeter much, or not at all? Is it insignificant?
It depends, right? So typically, yes, when you cross a front, you will see a significant change in pressure. As you cross a front, the temperature will probably, the pressure will probably drop, because all fronts, like we said before, lie in troughs, and troughs are lines of low pressure. So as you cross through the front, you might see a drop in pressure. But depending on the type of air mass you're going into, you may see a drop again as you pass through it, or it might go back up. So, again, if you're VFR, you are required to update your altimeter every 50 miles. So you should keep adjusting your altimeter as you cross through these fronts. But yes, like to answer your question, you could see a significant change in your altimeter.
Yeah, cool. Thanks, man.
No problem. All right, everybody. Oh, you got one more question?
Yes, sorry. What would be the best way to find the altimeter settings at every 50 miles?
Every airport, at least in most sims, even and in the real world, they'll have an ATIS frequency or a weather observation frequency. Plug that into your comm radio, and it'll give you the local altimeter. All right, guys. I look forward to seeing each and every one of you next week, and I hope you guys enjoyed.
Thank you.
Yeah,
No problem,
thanks,
guys.
man.
Have a good one.
Doing this.
No problem, guys.